A little bit of background on Shopify. Our booth is just outside the door, but if you have no idea of the context I'm going to be talking about, we are a Canadian-based e-commerce company. We are definitely not a startup anymore, so we have over 3,000 employees. As we are an e-commerce company, we have over 600,000 merchants selling products on our platform. And if you like Kubernetes like me, one of the nicest examples of using Shopify is that if you go on the CNCF store and you buy a Kubernetes hoodie, that's going to be served by our Kubernetes infrastructure. So CNCF store is hosted by us. To give you a little idea about our scale, our main application does about 80K requests per second during peak times. So that should kind of give you an idea of the problem domain and the scale we are talking about. To start on this journey, we have to jump back a couple of years back. So in 2016, two things happened. We lost the great artist David Bowie. But on a more positive note, Shopify was doing really well. We were gaining more traction, we were getting more customers, we were getting more global customers, and also as a company we were really monolith-focused before, but in 2016-ish, we started building more and more features and kind of an ecosystem around our monolith. So it wasn't anymore about that single Rails application, it was more about a suite of applications, some of them Rails, some of them something else. So we ended up in a situation like this. We had our own data centers. We were using Chef as a configuration management tool, and we were also running Docker in there. We were actually one of the first non-trivial production users of Docker, and we really loved that technology. In addition to that, we had a PCI environment in AWS that was using just Chef, not Docker. Then we had various different environments in AWS that were using Chef, maybe Docker, maybe something else. And we were also growing a lot on the Heroku side. So by default, if somebody wanted to create a new application, that would be hosted on Heroku. And because we didn't have a good story of how to kind of migrate from Heroku to somewhere else or how to kind of mature from Heroku, things actually stayed there for quite a bit of time. On a positive note, Heroku does a good job on this. So you can actually run quite non-trivial amount of traffic on Heroku without much operational work at all involved. At the same time, we were involving more process into how we want to classify these applications. So what we came up with was these 4 different buckets that we call tiers. And each of our applications belongs to a single tier. The higher you are on this pyramid, the higher your application's impact is on our business. So tier 1 application means that if the tier 1 application is down, most likely you cannot buy anything from Shopify. And what that means for our merchants is that if the merchants can't sell anything, their livelihood is in question. So we are dealing with people's livelihoods here, and we take that with seriousness for sure. Tier 2 could be something like fraud detection. So if it's down, it's a really serious thing, but people can still buy those sneakers and buy those hoodies of our platform. Tier 3, something like internal applications, something external maybe, but with low impact. Tier 4, hack-days applications, garage applications, prototypes, MVPs, whatever. So higher you go, the more important you are. And on another level, the higher you are on the tier, the more we require out of you. So we introduce requirements like regional redundancy, pager rotation, CI, pingdom. Based on the tier, we expected you to hit these checkboxes and make sure that you fulfill those requirements to be actually classified as a higher tier and kind of mature on that level. This model of having really random environments that look different, work differently, was set up differently, and involving that process that has some requirements wasn't really scalable anymore. Like you can reason about like backups, like what does it mean to have backups? What's the retention time? Can you actually restore them? Is there automation test that the restore works? And this was the discussion we were having inside the company, is that we have to have some sort of uniform story to actually talk about when running applications. So things that really didn't scale was any kind of manual or artisanal process. So somebody needing a new environment at AWS had to go and ask the operations folks for putting up EC2 servers or whatever else like manual process like that. And it's also slow if you have to wait for a human to take any kind of action. At the same time, we were really heavily involved we were heavily invested in Chef as a configuration management tool. But if you are familiar with Chef or Puppet or basically any configuration management tool, you probably know that those get out of date really fast, they get rusty, they get kind of wobbly. So when you build a cookbook, it might work ideally in your happy story, but 2 months later somebody tries to reuse that cookbook for something else and it just blows up on their face. We actually had a playbook for setting certain environment in 2016 that as the last step had a Chef bootstrap marked as the step, and it has a little notification that most likely the bootstrap won't work on the first time, but you can just run it again, and the second time it will 90% of the times probably work out just fine if you retry it again. So things like that aren't really scalable for big companies, but even smaller companies really. We kind of knew the things that we needed to do to fix this issue. So we needed to introduce more testing practices in our infrastructure. So for example, testing those cookbooks, especially in integration level. So we actually built a tool that would spin up VMs, do those Chef bootstraps, and make sure that they are always working the same kind of way. But that's still kind of, it's better than nothing, but that in itself was quite wobbly too, so we were getting false positives quite a bit. Really heavily, we knew that we need to heavily invest in more automation, so those operational workflows and traditional operational ways of working just don't scale anymore. And as we grew as a company, we were onboarding a lot of developers, like tens of developers each month. And the more you have developers, the more you have applications, and thus you need to build more environments and more environments. So again, asking operational people to do something just isn't scalable. On production engineering side, we wanted to invest in certain technologies we wanted to be experts of. So rather than everybody being a generalist and understanding MySQL, understanding how transit networks work, how hardware works, how Chef works, how whatever works, like understanding that all is impossible for a single person. You might know a little bit about everything, but you are not really an expert of any of those things. So we refactored our organization inside production engineering into sub-teams so that we would have a team dedicated to be really heavily experts on MySQL, a team that would be experts on traffic, a team that would be experts on something and something else, so that we could grow those experts inside our company. We decided that we needed some sort of platform to get these things done, get those self-serve aspects, get those tested infrastructure things, and this is basically what we ended up with. So we wanted a single story to build, we wanted a single story to run, and this quote really echoes really well what we wanted to do. So bring all those applications into a single place where they work just like other applications. They work uniformly. So if somebody moves from team A to team B, they will be familiar with all the tooling that's involved in the application runtime and application environment. For building a platform, we had 3 major principles. So first principle was that it has to be a paved road. Again, when you're trying to hit a self-serve system for developers, you want to make sure that it works perfectly every time. And nothing obviously is perfect, but compared to something like Chef, where the last step of playbook is that try again, that just isn't something you want to introduce into a platform. Like if you use Heroku and Heroku would give you a notice that please try again, if it didn't work out, you would probably not use their product, right? Another big thing is that as we knew that we are building something new, we are laying down this asphalt, we could kind of specialize and make sure that the asphalt is ideal for our use case. So there's different kind of tarmacs that you use for racing circuits, and there's different kind of tarmacs that you use for general roads, and that's the kind of idea we took, that we can kind of be opinionated about the type of tarmac that we are laying down. Also, continue with this road analogy. Last but not least was that we also wanted to build inside this road guardrails. So we had really good experience from Shopify Core, our main monolith, about resiliency platforms, backup stuff, all that kind of patterns and best practices. And we wanted to make sure that we built those best practices as guardrails into something that everybody using this platform could use. Second principle was hiding complexity. So when you're building a platform, by nature, it's going to be complicated, especially if you're trying to solve three different problems, which are runtime, deploy, and setting up the environment. So we wanted to make sure that we don't require our developers to be, like, we didn't want to make the developers operational people. We do DevOpsy kind of things, but we don't kind of expect them to understand this at this level. So we wanted to hide all those technical bits and pieces underneath them and make it as smooth as possible. So the experience would be kind of close to something like Heroku, but obviously we are not trying to build a Heroku alternative ourselves, but we were kind of opinionated about hiding that complexity and making sure that the developers don't have to battle that cognitive overload of understanding what Kubernetes is, how it works, what's everything else, how does our build system works. It would be a platform that they just consume rather than have to build themselves or debug themselves. And self-serve. This was really one of the cornerstones that we wanted to solve, is that nobody likes to create issues and wait for somebody else to react to that issue, like be it a Jira ticket, be it whatever. Nobody likes to do that. In general, in my opinion, or in my experience, people don't even necessarily like to talk to people. So if you can ask the computer to do something for you via an API, via a web UI, be it whatever, that's usually the more pleasant experience than going to some person and asking them to do something for you. So self-serve was the third and one of the biggest cornerstones that we wanted to solve. Okay, so we have these 3 principles now, and it's time to start actually designing and building the system. So when you start building something, you need a solid foundation. You need something that you build upon. It has to be the most stable and most important part of whatever you're building. It doesn't matter if it's a frame of a car. It doesn't matter if it's the foundation of a house. It's always that foundation has to be solid, right? So in our case, we looked into multiple different container scheduling systems, multiple different platforms. We were even playing with the idea of something like OpenStack inside our own data centers. Kubernetes eventually came on top because it had the best traction of the open source projects. Also, something like OpenStack, especially in 2016, didn't really solve the problem of container scheduling. So we really like Docker, and we've been using Docker for 2 years, so we knew how containers work, and we really knew what they are good at. So we wanted something that would be good at handling containers and just containers. We needed to make sure it's platform agnostic, so we were really afraid of choosing some solutions that would lock us into a vendor. So Kubernetes is great because it's open source. You can run it yourself. You can run it on different kind of operating systems. You can do all kinds of sorts with it. Or you can get it like hosted by vendors like Google or Amazon these days. So it's really great because you can choose and pick what kind of approach you want to take to this technology. And if 2 years later, 3 years later, 5 years later, you want to make a change in where you want to run it, you can definitely do that, and you don't have to go through a huge migration of changing your whole platform. Kubernetes also was and still is one of the most extendable solutions. So our team was formed from software developers, and we knew from the get-go that whatever we choose would have to be something that we can extend. And by extend, I mean writing code on top of it. So in terms of Kubernetes, and I'll touch this on later, it's going to be Kubernetes controllers, but this kind of extendability in a native way was one of the huge reasons why we went with Kubernetes. And it was written in Golang, which we had expertise in-house. So again, Docker is also Golang. Most of the infrastructure tooling is Golang. We were also building applications inside our company that had nothing to do with infrastructure that were in Golang. So we kind of had that expertise in-house if and when we needed to do any changes. And Google offered this as a service, and how we actually got started was a Hack Days project 2016. So we wanted to kind of test out how much effort it would be to run Shopify Core, our main like massive monolithic application on top of Kubernetes. And if you would like go with something like Kelsey's Kubernetes from scratch, you would probably spend 2 days just setting up the environment to be runnable for something that massive and complicated. So we went with Google Cloud for the Hack Days project. We really liked how it went. We were able to run all our stateless workloads on it inside 2 days, and actually at non-trivial scale, so we were able to also benchmark it. And after that, we kind of had a good idea what kind of issues we have to solve, and what are the issues or what are the features that we are kind of gaining out of this solution. So now that we have our foundation, the next step is kind of build on top of that foundation, right? So building blocks to actually have those environments that people can use, and which will eventually mean that the developer can have a public endpoint that our customers can hit and enjoy. So how to specify your app's runtime, how to build your application, how to deploy your app, and how to set up your dependencies. And by dependencies, in this case, I don't mean anything like JSON packages or Ruby gems. I mean more about databases, SSL certificates, DNS records, keys to do encryption, keys to talk to somewhere else, and that kind of dependencies. So I'll go over these 4 points and show how we've kind of solved these things. The first is creating an application environment. We already had a tool called Services DB. That was just a service catalog of all our applications, metadata about them. So in Services DB, you could go and see an application like our fraud detection system is called Blade Runner. You could go and see what teams owns Blade Runner, where are the logs and metrics for Blade Runner. But we extended this in a way where Services DB would also know about the environments and, most importantly, be able to create those environments. On Kubernetes side, we created a small tool called ground control, and that's just a tool that builds scaffolding for those environments. So it listens to Services DB calls on an API, and it creates the Kubernetes namespace, it creates the encryption keys, service accounts, whatever is the basic scaffolding that we need for all of our applications. And Services DB also, after setting up the environment, also handles setting up the build system and setting up a CI for our applications. This is a good, quick example of how Services DB works. So on the left corner there's a screenshot of Services DB and an application called CumulusCat in an environment called Niko. And there's a create cloud runtime button that the developers use. They get a new page that they have to kind of look through, and there's only a few things that they have to care about. So they pick and choose their stack, be it Rails, be it Golang, be it something else, and then they can specify the workloads they will be needing. So workloads is the same thing as dependencies in this context. So do they need asset uploading? Do they need something like a MySQL database? Do they need SendGrid API keys to be able to send email? So all those kind of things are just add-ons, quite similar to how, for example, Heroku works. But in our case, what actually gets generated from these are Kubernetes templates. And all of those dependencies are actually, or most of them are Kubernetes custom resources, or actually third-party resources back when we started out. OK, so now we've generated that environment, but our application is still sitting in GitHub. No Docker image has been built yet. So the next step is actually figure out how do I build my image. And for this, we leverage our CI tool called BuildGuide. If you are not familiar with BuildGuide, you can think about like Jenkins or whatever else tool like that. It's the same idea. Underneath BuildGuide, we have a custom tool called Pipa. And Pipa is just the application that actually knows how to build images, where to build them, and we created 3 different build pipelines inside Pipa. So most of our applications leverage Heroku-ish, because again, like we had hundreds of applications in Heroku that we wanted to migrate into this platform. So we wanted something that the developers would be already familiar with, like build packs and stuff like that. Heroku-ish is the open source version of basically that abstraction layer Heroku has created of auto-detecting. If you have a package.json inside, you probably need to do npm install. If there's a gem file, you probably need to do bundle install during your image build time. So those are the kind of things that we get free from Heroku-ish. And this has been working really well for us, because majority of our applications don't have any Docker files or any kind of instructions on how to build that application. Heroku-ish just figures out how to actually do it. And on our side, as we offer Heroku-ish, we can, it's open source, we can do any kind of opinionated changes that we want inside of it, specify the Ruby versions that we want to use, specify the Golang versions we want to use, any kind of stuff like that. And the last one is kind of legacy. It's a custom build pipeline that we use mostly for Shopify core. There's legacy reasons, but basically one of the things is that we did really heavy caching for Shopify core. Again, story of a monolith, you need a lot of caching. So now that we have our image, the next step is going to be deploy. um, Kubernetes deploy is an open source tool. It's a Ruby gem, but what it does, it's basically a really fancy wrapper around kubectl apply f. So kubectl apply f, as those that use Kubernetes probably know, is an asynchronous tool. So you ask the Kubernetes to do something, but you never know if it actually did that. So you ask for a state, but you just expect it to happen eventually, or you need to ask it manually if it's actually in that state that you asked for. Kubernetes deploy solves this problem by doing the kubectl apply f, but after that, looking into those new change resources and making sure that they are actually in the state that you wanted in your template. So think about a trivial example would be like deployment. If you have 3 replicas and you change the image, so you deploy the new version, is the new deployment healthy? Did all the replicas come up? Are they serving traffic? That kind of stuff. We also needed to add a bunch of logic into protecting some namespaces and also fix some egg chicken problems. So for example, your application might be requiring secrets, configuration maps, stuff like that. We need to make sure that those get deployed before the application deployed, so you are in a sane state when your deploy is finished. This is a highly pluggable tool, so we still wanted to leverage our old deployment tool, which is called Shipit. It's also open source. But as Kubernetes deploy is just a binary that you call, you can plug this into Jenkins, you can run this manually on your laptop, like the screenshot is showing here. But in our case, it's part of our deployment pipeline. So this is not how we do deploys in Shopify. This is just an example how a developer can run it on their machine. So if you use Jenkins and if you like something like that, check it out. You can literally just put the binary in and start using it. And last is those dependencies. So I'm going to touch more on this because this is the most exciting thing for me personally about Kubernetes is those custom controllers. We created a framework called Cloud Buddies. Cloud Buddies is just our internal term for custom Kubernetes controllers. So we created the same thing that I've seen at least 5 other companies do, which is looking at ingresses and creating DNS records. Based on that, we also fetch SSL certificates. We create buckets with those custom controllers, databases, services. So all those dependencies that the developers might need, Redis, memcaches, whatever. On the other hand, on the infrastructure side, we've also found this workflow really valuable because we can create infrastructure concerns like setting editable quotas automatically and being opinionated about how those quotas rules and security rules and all that kind of stuff can be done via the custom controllers and can be super dynamic. And the controller is inside the cluster, so it knows the state. So it's not like you are running a script against something and you assume that the state is something. These kind of controllers can actually look at the state and try to get you to the state that you expect to be. And if there's any problems, you can write that code inside your controllers and kind of be prepared for those problems. Because as we all know, there's never a happy story. There's always going to be something that doesn't work out like you kind of expected it to work out. And last is kind of like, you can create stuff like, in our case, node buddy, which look at node conditions, and if there's node conditions that we deem to be bad, Docker is stuck, network is in bad state, the controller can just delete those nodes. So we use GKE, so we just call the GKE API. So we first train the node, and then we call the GKE API and say, hey, this node is done, please delete it and give me a new one. We have 20 plus of these controllers right now, and you can probably kind of guess what these controllers do based on the names. So bucket buddy, cloud SQL buddy, mail buddy, memcache buddy, RBAC buddy, quite self-explanatory what they do. But one of the greatest things inside our company is that I work at the cloud platform team, and I've written multiple of these, and originally we were the team that were writing all of these, but right now it's more about different teams adopting the controllers and building the controllers that their teams need. So for example, I have a colleague here called Sam, and Sam's team handles our Kafka infrastructure, and they are responsible for Kafka access buddy, stateful buddy, and they've been writing them themselves. Even one of our teams outside of production engineering leverage this same approach, the identity buddy, where they can use the same CRs to kind of make it so that if another project needs an API key to talk to another service, they can use custom resources to ask for that access. To give a little bit concrete example of this, if somebody is not familiar how custom controllers work, they are just Golang applications. So in terms of like name body, we are dealing with a Golang application that talks to two APIs. So name body is running on the cluster. It talks to the API server API. It creates a watcher and watches for any events on ingress objects, create, delete, update. It looks at the ingress objects metadata like host fields, and based on that, it calls, in our case, Google Cloud DNS API, but whether, it doesn't really matter what API that is, and creates, edits, updates, whatever, those DNS records. So our original implementation of this was less than 100 lines. Like, it's super easy to get started. It's super easy to kind of create an MVP for whatever kind of automation you need. So this is a really great thing to kind of get started with. It's really easy to understand. And as it is just an application that talks to two APIs, any kind of workflows that you have around unit testing, integration testing, you can introduce here. So no longer is infrastructure tooling something special that is kind of separated from normal application workflows. You can just think about this as another Golang application that just happens to be talking to infrastructure services or infrastructure APIs. So if everything went fine, so we've gone through those 4 steps, this is what our developers should be seeing. A public endpoint that anybody on the internet can hit. It's SSL certified, DNS is propagated, the cat picture can be in Memcache, Redis, Cloud SQL, whatever backend they choose, and they don't really have to care about manually setting up anything, asking for operations people to do creating an SSL certificate, creating DNS, anything like that. This is totally self-serve, and this is what they end up with. I want to talk a little bit more about these bodies and controllers because, again, this is the thing that got me most excited about Kubernetes. So it's all about extending Kubernetes, and it's really easy to get started. APIs are really well documented, and there's like 100+ blog posts probably at this point about how to write your controller, how to get started, and I think even Google has released multiple really high-quality ones, so it's really easy to kind of get started and understand. The client libraries are really high quality. We've mostly worked with the Go version, which is client Go, but there's also Ruby implementation we use in some places, and both of those things are working really well for us, at least. So compared to some APIs we've used from other vendors before, these are actually the better ones I've dealt with. We can extend the functionality of the concepts that already exist in Kubernetes. So for example, NameBody deals with ingress objects, which is a built-in object type in Kubernetes. But we can also create our own object types for our own purposes. So these are called custom resource definitions. And there's also distributed system primitives built into the Kubernetes API that you can leverage. So things like leader election, latches, not something you want to be writing, at least not something you want to be writing every year yourself, but it's more about something you want to leverage, and especially if you have a system that already deals with this, you just want to use them rather than build them yourself. So these are the things you can get from free from using these APIs. Even if your application doesn't deal with Kubernetes or infrastructure, you can still use Kubernetes as a leader election or latch mechanism. And yeah, again, pure Golang, unit testable, running, and deployed as normal applications. So if you are familiar with something like, again, Chef or Puppet, there's no custom DSL or no special library that everything goes through. It's just these Golang applications. To kind of nail down on this point, Kubernetes controllers are as simple as in a loop, basically, well, watchers, but technically in a loop. They look at the desired state. So if there's a new object, updated object, or a deletion on an object, that's the desired state. Then we look at the current state. If those two don't match, we reconcile. And the reconcile function here is the thing you have to create yourself. But that's also the interesting part, because that's totally up to you what you want to do. So if an ingress object gets updated, you can do whatever you want. You can send a Slack message, you can send your mother flowers via an API, you can do whatever you want based on those object types. So you are totally free to do any kind of automation you want, and you have all the data available to do any operation you want on that metadata. And the workflow is always the same thing. So you authenticate against the cluster, you create that watcher for the object type, you handle those events, and that's it. So again, if you write one controller and you need to do another controller, it's so easy to kind of do the same thing and just focus on the business logic that you have to put in the reconcile function. Those custom resource definitions is something we really heavily bet on too. So we started with third-party resources, which was kind of predecessor to CRDs. But what it only means is that you introduce a new object type into Kubernetes. So you can create object type like Memcache, Redis, Mail, my mother's flowers, whatever you need in your use case. In our case, we have an object type called pingdom shop, which means that we want to create a pingdom check for a new shop. But it can be whatever you want. And you can be, again, watching those events, watching those custom resources, and do whatever you want with them. On templating side, where you developers might be seeing them, they look just like normal deployments or services. So again, no custom DSL, nothing custom. It's just the same kind of thing that they would be seeing with building Kubernetes types. Here's an example from, I think, Getting Started Guide or something like that on Kubernetes. And you can see a deployment object in here. Spec has 3 replicas. The container spec has, it's going to be Nginx, it's going to be this image, container port. So this is all the information that the deployment controller needs to do to actually create those running containers for you. This is our version of Elasticsearch object. So if you compare these two, they look just the same. So our developers don't necessarily have to understand how Kubernetes work. The only thing they care about is all these variables, what they do, what values is there, and what they want to do with it. So for example, there's Elasticsearch version. If our developers want to use 7 instead of 6, I'm not familiar with ES, by the way, so I don't know if 7 even exists, but if 7 exists and they want to upgrade, they change the number 6 to 7, the update call comes to the controller, and the controller can then, in the reconciliation, do whatever it wants, however gracefully, however you want to do those operations. And on the flip side of things, think about setting up Elasticsearch cluster with raw templates, with deployment services. How do I reveal the Elasticsearch? How do I set authentication models? All that kind of stuff. This would be hundreds of lines of YAML if there wasn't an abstraction layer. And even still, you would lose all those custom update functions and all that kind of stuff. So this is a really nice abstraction, both for developer folks and on SRE/production engineering side, also for those people, because then we can argue about, not argue, but be opinionated about how we want to do certain operations underneath. So there's always the case that you haven't covered all the use cases with your self-service system, or that something just goes wrong. So we didn't want to introduce the cognitive overload of introducing Kubernetes to our users. We wanted them to be using more of a platform, more of an abstract thing, but we still recognize the problem of people needing to do basic operational stuff. So the Cloud Portal is a web UI that the developers can go into. They can only see their own applications, which also one-to-one map to namespaces, and they can see their deployments, ingresses, they can see their ingress IPs, they can exec into containers, they can restart containers, stuff like that. This is a good abstraction because kubectl is a command line tool. So if you need to do an operation, you need to learn the concepts and the exact command to do something and what that does. If you have a web UI, it's a lot more easier to kind of find out stuff. So you can just click around and, oh, it's an ingress. What does ingress actually mean? Because again, not everybody even knows what ingress means. But if you go in there and you see that it's an Nginx with this IP, you kind of recognize that it's the same thing as a load balancer. And on deployment side, like if they need to, for whatever reason, go inside the production via exec, they can totally do that, but in a safe manner without us giving them more access or more complex tooling to do that. So this has been hugely popular inside our company, and it's also an easy way to kind of bridge that gap between our abstraction level and the Kubernetes concepts. Documentation is something we also put a lot of effort into, and in our case, the documentation is more about answering those questions of how do I do X, so I need to use a CDN, I need to do asset uploading, I need to understand the ingresses, I need to do something with my application. This documentation tries to answer those questions. So how do I asset upload? How do I get on database? That kind of stuff, rather than being in documentation on how we built this platform and how does it work underneath, where's Kubernetes, what's this tool, that tool, where they live. This is not the case. It's more about answering those questions. And internally, we were able to also pull in technical writers to this documentation project because we recognized that this is going to be hugely impactful inside the company. This needs to be A+ quality. It cannot be something that I wrote during my morning coffee when I was rushing into a meeting. This has to be A+ quality that is easy to understand and consume, no matter if you are intern, not even understanding what containers are, or if you're a senior developer that needs to do some really exact thing that they know what they need to do, but they don't just know how to do it. And when the documentation and self-serve portal fails, there's still help on-call rotation, and we did this a little bit differently. So originally we had a cloud platform team being on call and being cloud help. So we were helping our users to migrate any problems they had. We tried to help them out. But we were able to pull up support person for our support organization inside our cloud platform team. She's Jenna, and she's been amazing. So why this is a good idea and something I would love to see in other places being done is support persons are expert of that domain. So they are interested, they are empathic to the customer needs. They know what data is relevant to kind of collect. So if there's certain things that pop up all the time, they know how to collect and aggregate that data and make sure that it gets propagated back to the people caring about it. And they just are a lot better in terms of supporting people than generally developers are, because developers are more focused on fixing the exact thing, and they might be jumping into technological solutions, whereas support persons are thinking more about a holistic view of what's actually going on, what's the users need, how are they feeling, how urgent is this, and stuff like that. The secondary layer in here is actually still our cloud platform. So if Jenna doesn't know how to answer something, there's a second person from our team that can bring in that expertise on if there's, and in case of emergencies, it's really useful to have a subject expert to help out. So how did we do? The turnaround time to getting an app running on cloud platform is unreal. You folks have really nailed it. This is an amazing feedback that we got a couple of months back, and I personally really love getting good feedback like this. And it's exactly talking about the things we wanted to solve. So how do developers get their application as fast as possible, production grade, production quality level into their actual usage? On a more negative level, the challenges we had. So how does my builds deploy everything work? So creating abstractions means that, yeah, it's abstracted, so it's not something you can Google up. So we still have a lot of work to do to make sure that people understand enough so that they can make good decisions. Scaling, if you're familiar with Heroku, you know there's sliders, autoscalers, all that stuff. Again, our system is different. How do they do that? How do I debug? Some people that come from traditional enterprises are familiar with SSHing into production. We don't offer SSH, it's working differently. And is this worth it? So how do you get buy-in from those developers? Why would they want to move to your new platform when they are working fine on Heroku or wherever? And we solved this problem by trying to offer something to the developers that they would want to use. So something that Heroku doesn't do, or something that they wanted to do but didn't know how to. So we tried to make it so that they wanted to get on this platform rather than us forcing and having deadlines that you have to be migrated at certain date or something like that. On SRE side, we were moving to the cloud from the data centers, so we were giving up a lot of control of transit networks, hardware, whatever else. We were also running stateful workloads on bare metal. So moving stateful workloads, Splunk, Kafka, whatever else to containers was also very interesting. And there's quite many battle stories about those. And on production engineering side, just like developer side, there's pressure of building features or acknowledging scalability issues or whatever else. So they would also have to, at the same time, migrate our infrastructure tooling into the cloud and still deliver those changes that were needed for our business. and just learning a complex system like that, because SREs, production engineers, need to understand how the engine works. That cannot be abstracted away from them. So the takeaways from all this: target hitting 80% of your use cases. So we had that paved road idea where we were focusing mostly on Rails and Golang. That solves 80% of our use cases. The 20% that are harder, we can either solve later, or we can do some changes that make it so that those go away. Create those patterns, hide complexity. That's really important because people don't want to learn complex systems, and don't restrict at the same time. And be conscious about vendor lock-in. So in our case, we are on Google right now. We are looking into multi-cloud and all that kind of stuff, but we know that wherever we want to go, as long as we can put Kubernetes on top of that, we can get this platform running in there. In the future, polishing out tooling, multi-cloud, service mesh, all the kind of nice stuff that is all the hype right now. Nothing too exciting, but it's more about making that platform more mature, more scalable right now. That we've actually gotten to kind of 1.0 at this point. That's it. Thank you.
Now we have a few minutes for questions. Let me run around elegantly.
Hi, first of all, thanks a lot for a great technical talk. Totally loved it. Thank you.
Thanks.
I have a couple of questions. So, Cloud Buddies controllers, are they open sourced?
No, it's unfortunately not open source. So we kind of made the mistake of making this internal framework so opinionated about Shopify-specific stuff, so it's really hard to open source at this point. But this is definitely something we've been talking about and with other companies, because like the NameBuddy example I gave, that's something that at least 5 other companies have basically created, the exact same thing. So if this was open source from the get-go, maybe those 5 other companies wouldn't have to create the same tooling, or we wouldn't have to be creating that tooling ourselves.
Got it, thanks. And the second one would be, there are several frameworks for creating custom controllers and CRDs, like Meta Controller, Operators Framework, KubeBuilder. Do you use any of them?
We are looking into that. We are using stuff like auto-generation, but no other frameworks. So a bunch of the stuff that are in these new frameworks obviously the frameworks didn't exist in 2016, but a bunch of the stuff that they solve today, we've had to build into Cloud Buddies. So yeah, it's one of the things that are in back of our mind, to deprecate the Cloud Buddies framework and go more of an open source route, so we can also open source this stuff, because part of them are not useful for other people. Ping.Don't Shop Buddy doesn't apply to any other company, most likely, but other stuff do for sure apply to other companies.
Right. Thank you very much.
Thanks.
Another question? Over there.
So you talked about writing these Kubernetes controllers. It's code, so if you're unlucky, you introduce bugs. Have you had any problems with debugging it when it did go wrong?
Yeah, absolutely. So this is where the tiering system helps. So how we model our clusters is that we run n amount of clusters per tier, and we try to test as much possible on terms of unit testing, integration testing, but also when we roll out something that we deem scary. So for example, if you do a change in the Cloud SQL Buddy which deals with our databases, we roll it out first to tier 4. So if our Hackdays applications databases blow up, that doesn't concern anybody. If in tier 2 or even tier 1 our databases blow up, that's going to be a service disruption. That's going to end up with Shopify being mentioned on Reddit. So that's how we try to make sure that any changes we do are as safe as possible.
Time for one more.
Thank you. 2 quick questions. How long did it take to do this migration? And second question is, what is the current adoption rate of Kubernetes in Shopify?
Yeah, so there's 2 separate things. So we still have a huge monolith, and migrating that took probably over a year. We were moving, so we are sharded by shops. So we were moving shops, like smaller shops first to the cloud, and less impactful smaller customers And we were gaining confidence by doing that. But the bigger customers that have flash sales, which can be 100x time the traffic that the other shops create, those were really the hard cases that we left last. And just a few months back, we migrated last of our big customers on this platform. So over a year for Shopify Core, on all the other applications, I think that was probably also a year-ish, but we didn't have any. We wanted people to kind of do the migrations themselves. We didn't do anything for them. And obviously, because there's pressure to ship features, we didn't want to impose really strict deadlines for them, like you have to be on this platform in 2 months or whatever. We kind of wanted people to gradually get on the platform. This also helps when you're building this. Like, it's more about a moving car that you are trying to change tires at the same time, right? So it helps that there's not a huge influx of applications suddenly coming in, but they gradually come in, and if there's bugs, you can fix as you go.
Thank you.